All right, Georgie. Hopefully I'm going to be able to be a little bit of help to you here. I'm not going to work them for you, but I'm going to talk you through them so you can kind of see the reasoning that you need to develop. Um, the first one that I'm going to look at, because 1 and 2 are just conceptual, and I think you were fine with those, or you should be. They're just basic definitions. The speed of light, number 3 says the speed of light in the vacuum of space or in air is a constant of 3 times 10 to the 8th meters per second. You should memorize that value so you don't embarrass yourself publicly. It's something that anybody that has any knowledge of science should have that number in their brain. Speed of light is always 3 times 10 to the 8th meters per second. You'll probably never be asked to give that on a test, you know, to write down that memorized value, but it just helps to have those kinds of things in your head. Okay, so a light year is the distance traveled by light in 1 year. So what is this distance? So they're asking you for distance. I think y'all use an X maybe, but I'm going to use a D for distance, and I'm going to get a clean sheet of paper and kind of take a look at that with you, and then we'll come back. So if you know that the speed is 3 times 10 to the 8th meters per second is the speed, and that's the average speed. It stays that same the entire time. And you're looking for the distance that the light travels in 1 year. You should notice immediately that seconds and years are not compatible, but I can do some dimensional analysis just like you did in chemistry, and I've got to get how many seconds are in 1 year. Well, I happen to know that because I've done this forever. There's 31,536,000, I think, but we're not going to guess. I'm going to show you how I got that. So I said, well, there's 365 days in a year. There's 24 hours in a day. There's 60 minutes in 1 hour. And then there is 60 seconds in 1 minute. So minutes canceled, hours canceled, days canceled, and I wound up with the seconds in 1 year. Whoa. Hate when that happens. Let me see if I can find that little rascal. Frustration with this equipment sometimes. All right, so all right, here we go. So hopefully you learned dimensional analysis when you took chemistry. It's a vital tool. If you didn't, get your mom to teach you. Hopefully you did. But that should give me my amount of time in 1 year. And so if I know that I'm looking for the distance, I want the meters to be on the top. So distance is speed times time. Average speed times time in this case. So the average speed is 3 times 10 to the 8th meters per second. And then you have, I believe it's 31,536,000 seconds. 536,000 seconds in 1 year. So that should give you the meters per year. Should not be a big deal. All right. Then he also asks you to find how much time does it take for light to travel from the moon to the Earth, and so you're given the distance. This is megameters, 10 to the 6 meters, so you know the distance in meters, and you know the speed, so you should be able to get the time by simply taking that distance, speed, and time equation and saying, okay, well, if speed is equal to distance over time, then speed times time should give me the distance. Very similar to what we just did, so that should not be a big deal for you at all. All right, number 4 says a airport radar uses a reflection or echo of a radio signal to measure aircraft's positions. Suppose the position of a certain helicopter at 1 p.m. is 105 miles, 90 degrees from the airport. At 1:30, it's 48 miles, 90 degrees from the airport. Find the displacement. So you're just looking for the change in position. So it stayed on the 90-degree bearing, so all you need to do is figure out how much distance did it travel. Looks like to me it's going to be about 57 miles, but check my math, make sure I'm not bad. So the displacement would be 57 miles, 90 degrees from the airport. And average velocity is just displacement over time. And it looks like your time was 30 minutes, so you want to convert that to seconds and get miles per second or miles per minute. I don't think it really matters. Assume the velocity remains constant. And now they want to know where's the helicopter going to be in another 15 minutes. All right. So you can either give that position with respect to where it was at 1:30 or with respect to where it was at 1 o'clock. Okay? 5 says you're driving down a cart 55 kilometers an hour. The child's going to run into the street. It's going to take you 0.75 seconds to react and apply the brakes. How many meters will you have traveled before you begin to slow down? So if we look at that, 55 kilometers an hour. An hour is 3,600 seconds. So I want to get it out of kilometers. I want to change it to meters. So there's 1,000 of those little rascals for every 1 kilometer. So that gives me 55,000 on the top and 3,600 seconds on the bottom. So I can make that division occur, and that'll give me 550 meters over 36 seconds. And I don't have a calculator with me, that's why I'm doing that kind of stuff. And then you know that's your speed, average speed, and you know that distance is equal to average speed times time. So if that's your average speed, and your time is 0.75 seconds, you should easily be able to see how far your car is going to move before you can get the brakes to start slowing it down. Okay? Number 6 says, suppose you need an average speed of 100 kilometers an hour to arrive at a certain destination on time. Traffic limits your average speed to only 60 kilometers during the first half of the trip's distance. What must be your average speed in the second half of the trip to be on time? Well, let me think about this one now. You have a speed of 60 kilometers an hour, and that's going to give you you're going to be halfway there. And so if you need an average speed of 100, you've got to figure out, well, how fast do I need to go for the last leg of the trip. So what I'm going to do is I'm going to pause the recording for a minute and think about it, and then we'll start up again. All right, so I thought about that one, and I'm not positive that I'm right, but here's a thought. Okay, so you know that that the average speed Okay, so you know that the average speed you want to maintain is 100 kilometers an hour. And you know that average speed is the average of two numbers, final plus initial, over 2. So if I bring this 2 over to the left-hand side, I got 200 is equal to the final, which we're the final average speed, which we don't know, plus the initial, which is the 60 that they give you. So I would think that the final would be 140. And I think that the only reason that that works this way is because it tells you in the problem that this occurs for half of the trip, and this has to occur for the other half of the trip. So I'm thinking that's good to go, but you need to check with somebody and let me know if I'm right or wrong, because I certainly could be wrong. Wouldn't be the first time today. So let me move on. Okay, so this looks like we're talking about the graph of the motion of the hummingbird, and it says for the interval shown below, or interval time shown, determine the following. What is the bird's greatest distance away from the flower? So you're looking at how far is he away. It doesn't matter which direction, so you should be able to read that off your graph. What is the bird's most western position? So I'm going to assume east is positive and west is negative, so you're looking down in here. Okay. At what point in time is the bird at the flower? All right, so you want no displacement when he's at the flower, so there you should be able to look at the graph and determine that. Determine the bird's average velocity. Total distance over total time would give you average velocity. Determine the bird's average speed. Okay, average velocity should have been total displacement over total time. My bad. And average speed should have been total distance over total time, because remember, velocity is a vector quantity, speed is a scalar. So all I want to do is look at distance here and displacement here. What is the bird's velocity at 10 seconds? Find your instantaneous velocity by taking the slope of your line. What is the bird's velocity at 5.5 seconds? Same thing, slope of the line. At what position is the bird's velocity equal to 0? So where there's no displacement, since it's a velocity, what is the bird's maximum speed? Total distance over total time. Okay. Again, refer to the above graph. Moving with a constant velocity at what point? So now you're just going to go back and pick that off of there. The bird is accelerating at what point and you're looking for a curve for acceleration on a distance versus time graph. Remember, it's always a curve if it's accelerating. The bird speed is decreasing at what points in time, so you're looking for a negative slope where it's slowing down. Answer the following and explain or give an example. Speed equal to 0 and at the same time an acceleration not equal to 0. Think about when you throw something in the air, when it reaches the highest point, the speed goes to 0, but it's still accelerating. Gravity is still pulling on it. Can an object have a constant speed and a changing velocity? So remember again, velocity is just a change in position. So think about that. Something goes around in a circle. It could have a constant speed as it goes around in a circle, but the velocity would always be changing because the direction would be changing. Could an object have a constant velocity and a changing speed? So could it be moving in the same direction but slowing down or speeding up? Can an object be moving but not be accelerating? Think about your cruise control. Can an object have a velocity and acceleration vectors that point in the opposite directions? Yeah, if it's slowing down. All right, so think about those kinds of things. Those aren't the only right answers, but definitely think about those kinds of things. All right, let's look at this one. Okay, it says a VW is going to go from 0 to 60 in 75 seconds, average rate of acceleration, and then it wants to know, assume a braking deceleration of 9 meters per second squared, so you'd make that negative 9. What amount of time was required to return from 60 to 0. So you got to be careful here. Make sure you use the meters per second. And we'll talk about how it actually works. Let me see if I can pull up my little... There we go. So what was it? 26.8 and 75 seconds. Okay. So the initial velocity was 26.8. Or maybe it was 28.6. Let's go with 28.6. You should always use your calculator to check my work because sometimes I do goofy things. This is the initial for me. Your guy might call it V naught and V original. Doesn't really matter. VF is 0. T is 75. And all they want to do is find the acceleration. Acceleration is delta V over delta T, or VF minus VI over change in time, so 0, because you're coming to a stop, minus 28.6, if that's what the value was, over 75 seconds. Should give you a negative acceleration, which makes complete sense. All right, now let's look at, then he says, if the brakes applied are acceleration negative of 9 meters per second squared, how much time was required for it to go from 60 down to 0, and it was 26.8, so I got to go back and do some fixing of some things. All right, so this one I did totally wrong because we wanted to start at rest. I apologize, I thought we were slowing down, but we're slowing down in part B. So this is 26.8, and again it takes 75 seconds for this to occur. So we want a positive acceleration. That's 0. So basically you have 26.8 meters per second over 75 seconds. And that's going to be around 0.3, 0.3, and it'll be positive. Use your calculator and get that value. And then part B says now we have a negative acceleration of 9 meters per second squared. And we want to go from an initial speed of 26.8 to a final speed of 0. And I believe we're looking for the time, but let's go back and look at the problem. Yep, time. So my equation right here just gets rearranged in time. Time is going to be VF minus VI over A. So that shouldn't be a big deal for you. You can handle that. All right, then you know the initial speed, you know the acceleration, and you know the time is 15 seconds, so you got to find the final speed. Not sure which equation you got, how he's going to write your equations, but I would say VF equals VI plus AT. and you know everything here. If you'll list your givens, hopefully you're doing that when you're working your problems. My VI is blah, blah, blah. My acceleration is 18 meters per second squared. My time is 15 seconds. And I want to know what is my final speed. If you will write your knowns down, it certainly will make your life a lot easier. I know it takes time, and they're so easy, but they get harder, and it's very helpful. So just get into the habit of doing that. All right, so we can find the final speed and then Mach number of its speed. So you're going to take that final speed and divide it by 330, and that'll give you your Mach number. In the 1940s, rocket-powered sleds were used to test responses of humans to acceleration. And so we're going to go 222 meters per second in 2.10 seconds. And so we can find the g's here. We know the initial speed was 0. The final is that. We know the time, so we can find the acceleration for when he's speeding up. And then we can take him from 222 meters per second down to 0 in 0.9 seconds. And so we have to figure out which one of those will give him the greatest amount of g's. And every g is the same thing as 9.8 meters per second squared. So if you figured that acceleration in number 12, and I'm just going to make up a number, if you found that acceleration to be 2100 meters per second, and you wanted to know how many g's that was, you would be dividing by 9.8 meters per second squared, and it would be really close to 200 g's, approximately 200 g's. All right, so let me see. I'm going to stop there.